of Newtonian-limit singularities in higher derivative gravity. And so you have 25 minutes, and please start as soon as you are ready.
Okay, thank you very much, and thank you for the organizers for the invitation for me to present these results on singularities in higher derivative gravity. This is the results I'm going to show today were obtained mainly in these papers that I listed here, especially in collaboration with Tiberio de Paula Neto, and more recently, Nicola Borzila and Leonardo Modesto. Part of these results were obtained when I was doing the PhD in Brazil, in the Brazilian Center for Research in Physics, and more recently here in the Southern University of Science and Technology in Shenzhen, China. I like the way these papers were organized here because they form like a pyramid, and I think this is a visual representation of the results because they started from a very particular case, and then we obtained more and more general results that I'm going to show now. So as I told you, I'm going to start from the regularity of the potential, then I will go to the regularity of curvature invariants, and then for the regularity of higher order curvature invariants. And also I will start from the local higher derivative gravity and then move to more general local higher derivative gravity and then non-local higher derivative gravity. And now it's good to talk today because many of the motivations for higher derivatives have already been discussed in the previous days. And so the main idea, so I will go very briefly on these motivations. The main idea for higher derivatives is because general relativity is not perturbatively renormalizable, and the higher derivative terms appear already when you do semi-classical gravity, that is, when you do quantum field theory in curved space-time. Then higher derivative terms with fourth derivatives of the metric, they appear as divergences of the vacuum diagrams that you have to regularize. And besides that, fourth derivative gravity is a renormalizable theory. This was shown by Estelle in 1977. And if you add more derivatives of the metric, you can have super normalizability. So higher derivative gravity with 6 and more derivatives can be super normalizable. Of course, as it has already been discussed a lot in this conference, higher derivatives bring the problem of ghosts, and this is still needs a definite answer, how to deal with the ghosts or how to live with them or how to make them safe. And there are many proposals in these directions. For example, in Lewick gravity, that is the higher derivative gravity with complex poles. There is the Fakion's prescription by Anselmi and Piva. Also, there is the issue of having unstable ghosts. So there are different approaches. I'm not going to talk about this issue here. I'm going to consider only the issue of the singularities in these models. And also to related to the problem of ghosts, there is the idea of having non-locality to avoid the ghosts from the beginning. And well, the general action I'm going to consider, it can be written in this form here. This is the Einstein-Hilbert action. You have here fourth derivative terms, and you can have terms with more derivatives here, or higher powers in curvature, or you can have even an infinite number of them forming like in a non-local theory. But as I'm concerned only with the singularities, the most simple singularities that we have in physics, that is the Newtonian singularity, the singularity of a delta source. I'm going to consider only this action here that can be, that is the most general for this purpose. You could add, for example, a term quadratic in the Riemann tensor, but it can be shown to be of order curvature to the 3, so it's not relevant. You can redefine your action to recast it in this form. So some results, older results, is that in the fourth derivative gravity, the modified Newtonian potential is finite. This is the expression. You can see that when r goes to 0, these coefficients conspire to 1, and then this 1 minus 1 cancels this 1, and you have a finite potential. And then the terms higher power on r. But still, the finiteness of the potential is not enough to cancel the curvatures, that the singularities that can arrive in curvature invariants. For example, still in the linear approximation, you can evaluate the Kretschmann scalar, and it has this expression here that still diverges, despite the potential being finite. And these calculations are all in the linear regime. You can also go to the nonlinear regime. This is much more complicated, and was done by Stell and the collaborators. I think maybe he's going to talk about that today, but there are still curvature singularities. Another result that was interesting is that in the incomplete polynomial gravity, that is, if you consider the action with the r and a quadratic in the Ricci scalar, here f1 is a polynomial on the D'Alembert, then you get a potential that is not finite. So my motivation is to further investigate the appearance of singularities in the Newtonian limit. As I told you, it is very complicated to do the analysis in the full nonlinear theory. There are many terms to consider. The nonlinearity is also very complicated. So I'm going to study the simplest singularities that are the Newtonian limit and the field generated by a point-like mass. So the action that I'm going to consider is this one. Here is the Weyl tensor. This is just a basis. You can choose other bases. It's equivalent. I'm going, well, if you have, if these functions here are polynomials, you have a local higher derivative gravity. If they are non-polynomial functions, you have non-local higher derivative gravity. Usually, this formula already appeared in this conference many times. So this is a standard form factor for the non-local higher derivative gravity. This is the exponential of an entire function, so that you don't have poles in the propagator, despite the usual graviton. This is the formula for the propagator. And these functions that appear here are related to the form factors in the action. And the roots of this equation define the massive poles of the propagator. So if you have a local theory, you have many degrees of freedom. Well, the equations of motion are these, and what we're going to study is the field generated by a point-like mass in rest. So we will consider a delta source, and we assume we can assume the metric to be static spherically symmetric, and the solutions are given by these potentials that we need to solve the equations. It is very useful to work with these auxiliary potentials instead of these original potentials of the metric, this chi2 and chi0, because they only depend on the spin 2 and the spin 0 part of the propagator. So if you solve the equations for chi, you can obtain the usual potentials in the usual representation. So this equation is very concise. It's good to work with this. And we're going to use the solution using based on the Fourier transform method. And you can write, as Jens just said. Also, I benefit from Jens' talk before mine. You can write this solution to the potential. And some examples. In the case of the fourth derivative gravity, we have this potential, that's the usual Newton potential, because a Yukawa correction. In a polynomial derivative gravity, you have further Yukawa potentials, and this constant that appears here, it depends on the masses of the particles in the spectrum. And in the exponential non-local gravity, the simplest non-local gravity, you have this potential related to an error function. And it's very easy to see that all these potentials are finite at r equals 0. But let's look closer to the polynomial case, because it is not so simple that it is finite at r equals 0, because you have these coefficients, and when r goes to 0, the exponential goes to 1, of course, and you need to prove that the sum of all these coefficients goes to 1. And this is an identity, the proof, general identity, the proof of this general identity can be found in this paper. And indeed, it works, and the singularity is constant. And these formulas here for the potential for a general polynomial derivative gravity are valid also if you have complex roots in the equation that is related to Leavitt gravity, for example. It is interesting because these complex poles, they generate oscillating contributions to the potentials that follow more or less the same lines that Jens mentioned in his talk. And some applications of these oscillating modes can be seen, for example, in this paper with Antonio Scioli and Ilya Shapiro. And well, with this result, using this identity, we can show that the metric potentials are finite for any complete polynomial derivative one. When I mean complete, is that it has higher derivatives in both spin 0 and spin 2 sectors. This was proved in this paper. But in this paper, we only worked with this result. We didn't actually evaluate the general potential for general models that could include, for example, degenerate poles. But as I already told before, the finiteness of the potential doesn't mean that the curvature is going to be regular. For instance, if you have this expansion of the potential, well, you assume that the potential is finite and is analytic, then you have this series expansion for the potentials. You can evaluate the linearized Kretschmann scalar, and you get this expression. And you see that there are divergences that depend only basically on this linear term on R. So we can say that a condition to have the regularity of this curvature squared invariants is that the derivative of the potential goes to over R goes to a constant. Or if the potential is analytic, as I assumed here, it means that the coefficients of these terms linear on R are 0. And also you can show here, I only wrote the Kretschmann scalar, but you can show that the same condition holds for R squared, Y squared, and so on. So we need to check the terms of order R to see if the singularity appears in the curvature or not. And in this work with Tiberio de Paulo Neto, we obtained the potential for a general polynomial derivative gravity, including the case of complex poles or degenerate poles. Our only assumption is that we have no tachyons. And well, this is a constant, this is a modified Bessel function. And you can expand this in, this constant depends on the partial fraction decomposition of 1 over the form factor. And you can expand the potential in power series and you get this result. And it is interesting, here is the coefficient of the term linear on R. It is written here. It depends on a specific combination of the masses of the roots of the polynomials. And you can show that if f, remember f is the original function here. that's related to the action. If f is of a polynomial of order greater than 1, that is a non-trivial polynomial, that is, if you have a theory of 4 derivatives of the action or more, then there is this identity here. And if f is of order larger than 1, that is, if you have at least 6 derivatives in the action, then S1 is equal to S2, and the linear term is 0. So if you have at least 4 derivatives in the action, you have finite Newtonian potentials. And if you have at least 6 derivatives, you have a regular Newtonian limit without curvature singularities. This holds independently of the number of terms here, and if they are degenerate or complex or real, and so on. So I'm going to call a potential without this diverging term as 0 regular, that is regular in the standard sense, and the potential that doesn't have the linear term on R, 1 regular. So we can say that higher derivative gravities with 4 derivatives are regular and have regular potential. It's at least 6 derivatives, they are 1 regular. 1 regularity means that you don't have curvature singularities. Well, I told you that you have these identities, and the proof of these identities follow from using partial fraction decomposition. This first identity, you can also prove it by brute force, as I did in the previous paper, but it's much easier to use partial fraction decomposition. All the details can be seen in the appendix of this paper here. But what happens in non-local models? Because so far I've showed that all the local models with more than 6 derivatives have nice regularity properties. And in some sense, we would like to extend it to non-local models, because you can see the non-local model as defined by a series of on the D'Alembertian. So it's like a polynomial with infinite order. Of course, this is not a good way of thinking, but it can be inspiring in some sense. And some non-local ghost-free models were known to have a regular Newtonian limit, that is without curvature singularities. There are many papers that did calculations to specific models. And so our idea was to apply the result that we had for local models to the non-local ones. So we used the formalism of the effective source that Jens also presented some minutes ago. That is, we pass this operator to the right-hand side, and we get a usual Poisson equation with a modified source. So here, instead of the delta, we have a semi-arid distribution. And we showed in this paper here that the polynomial theories with more than 4 derivatives, they have a regular source. And this makes the potential to be 1 regular, that is, without the term linear on R. And in the case of non-local theories, you can build, in some cases, you can build the effective source of the non-local theory as a limit of sources of local theories. You can do this, for example, in this ghost-free gravity of type N, that's defined by this form factor. And basically, you truncate the series, you get a polynomial function. So for each truncation, order in the truncation, you have a semi-arid source. And you can show that when you take the limit of this sequence of sources, it converges, and it converges uniformly. But of course, it's not true that it holds for any non-local theory. For example, if you consider some theories that which defined by form factors that tend to polynomials in the UV, then it may not happen, and the convergence may be not uniform, then you cannot pass the limit. This happens, for example, in this kind of, for this function here. So the result, some results for now, that we have now is that the regularity of the curvature invariants is not a consequence of non-locality or ghost-free condition. We can have local theories and theories with ghosts that have regular curvature invariants. And because actually it is a consequence of the propagator having an improved behavior in the UV. Also, Jens mentioned that this a few minutes ago. Here, I'm showing the proofs, let's say. And also, more recently, we studied the higher order regularity, because if you don't have the linear term in the series expansion of the potential, you regularize the curvature invariants without derivatives of curvatures. But it's not enough to regularize, for example, invariants of this type that have derivatives of the curvature. And this is in the static limit. For example, the box arc is related to this. This chi0 is the potential related to the spin zero part. And then, because you have this relation, you see that you can have a singularity here that comes from the 2n plus 1 derivative of chi0. So if this term is not 0, your singularity appears again. And the result that we got is that if your action has 2n plus 6 derivatives of the metric, then all the curvature derivatives invariant with at most 2n covariant derivatives are regular. So, for example, if you have n equals 0, then you have 6 derivative gravity, then the first term is in the series expansion of the potentials is r to the cube, then box r diverges. If you have n equal 1, then you have 8 derivative gravity. The first, you don't have r linear term, you don't have r cube, you only have r to the 5 and so on. So box squared r diverges and so on. This was proved in this more recent paper. And in the case of polynomial theories, you can see this explicitly for the most simple case of polynomial theories with only simple poles in the propagator. And basically, you have the function, that's a polynomial. You made partial fraction decomposition. You expanded the potential, and we need to see that the coefficients of the terms of odd power are 0 up to a certain order. And this is the relations that we get. So the previous relations that I showed are the first two cases of particular cases of these relations. This general formula was proved by Nicolas Bourdzila, who is a student in our group. And the result so is that if the action has 2n plus 2 derivatives, the potential is n minus 1 regular, but it is not n regular. So there is a certain order of the box of a certain derivative that you apply in the curvature that it's going to make some invariants to diverge. Well, the general theorem can be stated like that if the potentials chi are p plus 1 regular, then all the curvature derivative invariants with at most 2p derivatives are non-singular. I'm not going to go into the details. And this situation, this result can also be extended to some non-local theories, also using the effective source formalism that is very convenient. But here not as taking limits and verifying the uniform convergence of the limits, but in some situations you can derive inside the integral and pass the limit inside the integral, depending on the convergence of the damping of the caused by these form factors in the UV. And the conclusion is that, for more details you can check in this paper, the conclusion is that if the function asymptotically grows at least as fast as k to the 4 plus 2n for a certain n, then the effective source is at least 2n times differentiable, and all the derivatives of odd order with less than 2n are regular, so are 0, so the effective source is n regular. And then you can extend this to the potential. And so the potential in non-local theories with 10 polynomials in the UV are not completely regular. For example, you can take the Kuzmin form factor that's given by this expression. And in the UV, it has this behavior, so it depends on lambda. So if lambda equal to 1, you see that the potential, here we have the plot for lambda 1 to 5, and 1 to 4, and you see that for lambda equal to 1, the derivative is not 0. It is written here. In all cases, the derivative goes to 0 in the origin, but for lambda 1, it's not 0. So R is going to diverge, for example. If you take the third derivative, the one with lambda equal to 2 is not 0, so the box R is going to diverge in this case, and so on. Yes, I'm already out of time. So the conclusions are that in the theories with more than 4 derivatives in both spin 2 and spin 0 sectors, we have not only a finite Newtonian potential, but also a regular non-relativistic limit that is without curvature singularities. So in some sense, the divergences are softened when we go from 2 to 4 and to 6 and more derivatives. Also in the quantum side, we have a 2-derivative theory. General relativity is non-renormalizable. 4th derivative is renormalizable. 6 more, we can have supernormalizability. So in general relativity, we have singular potential and curvatures. 4th derivative, gravity, finite potential. And with 6 and more derivatives, finite potential and regular curvatures. And with more derivatives, even a regularity of a higher order scalars. So it's important to have in mind that the regularity of the curvature invariance is not a consequence of non-locality or of the ghost-free condition. It is a consequence of the behavior of the propagator in the UV. And even if you consider the regularization of the delta source, it can be achieved in local theories with 6 and more derivatives. But to completely regularize the delta source, that is that you can apply an infinite number of derivatives and, not an infinite number, sorry. You can apply an arbitrary number of derivatives that is going to be finite only in if you have a form factor that grows faster than any polynomial. That is that you have to have nonlocality. And this is, of course, only in the linear regime, but I believe that is a motivation for the investigation of the full theory in the nonlinear regime too. As far as I know, in the case of 6 and more derivatives, there is only one work that was done by Holden. Maybe he's going to talk more. So thank you very much.
Thank you for the nice talk. We have time, I think, just for one question. I think Philip was the first one raising the hand. So please, you can ask the question.
Yes, good morning or good afternoon. Thank you very much. The talk was very interesting. I wanted to comment on, first of all, the pure 4th order theory, just C² on its own. Dimos Kazanis and I have solved it exactly as a classical theory. And the exact potential is 1 over R plus R, the linear term, the one you later on got rid of, and I'll come back to that in a moment. But there's a general feature which says this: if you have del squared phi equals rho, the solution is 1 over R. Del 4 phi equals rho, the solution is 1 over R plus R. Del 6 phi equals rho, the solution is 1 over R plus R cubed. And the difference is, in del squared, the coefficient of the 1 over R is the integral of the second moment of the source. In del 4, it's the 4th moment. In del 6, it's the 6th moment. So it doesn't matter, as long as it's del squared and not del cubed. I don't know what happens with del cubed. But del squared, del 4, del 6, all of them are always going to give you a 1 over R potential, because that's already there if you just look at the Poisson equations. Now, those solutions, if you then plug them back into the equations of motion, if you just put the 1 over R, the Schwarzschild solution, back into the Einstein equations, you don't get 0. You get a delta function. And these solutions are not holding at all R. They're actually exterior solutions. They only hold outside the source. Inside the source, the behavior is different. And so I wouldn't be worried about curvature singularities at R equals 0, because there may be properties of the potential we wrote down, but they're never going to occur in any theory where you have a source which is going to give you a different behavior inside the source. So I don't think you need to be concerned about these Kreshman singularities, because they're not in the physical region.
Okay, thank you for your remark. Yes, well, the situation that we did here, we studied this field sourced by the delta. But of course, there is more general, there are other solutions, and I agree that it is important to look also for these solutions. But here our attempt was to see if how the higher derivatives regularize the delta. That is the most simple.
Mm-hmm. Well, yes, I mean, if you just stick a 1 over R into del 4, you'll get a delta prime. And if you stick it into del 6, you'll get a delta double prime. And that just means that you've got an extended source. You see, you can't have a point source if you have a higher derivative theory. You can have a point source for second order, but that's the special case. And it's not general that the source should always be a delta function. And the way to check that is to just take the solution and stick it back in the equations of motion and just look at the singular structure. And you'll see you get delta prime, delta double prime, and so on. That's there. I mean, that's a property of 1 over R in a higher derivative theory.
Maybe we can continue this discussion in the discussion section, because it's interesting, but we are running a bit late. So the next speaker will be